All right, where we at? What we doing? What's up? All right, so remember, a system of linear equations is a collection of equations that looks like this, and all of these are just matrix equations in disguise. Ax equals b, where a is an m by n, x is an element of Rn, and b is an element of Rm. Okay. So, as noted, these are wildly prevalent in not just mathematics, but pretty much all of the sciences. So, being able to solve this is not only mathematically interesting, but also makes us useful to the peasants. So, let's talk about it. Well, so the first thing we noted is that the only way a solution can possibly happen is if you are actually in the column space. If you are not in the column space, so if B is not a member of the column space, then this equation cannot possibly be solved. But in that case, the system is referred to as an inconsistent system. We will return to these in a little bit and talk about. It turns out that even if you're inconsistent, we can still get good enough answers. Depending on what your definition of good enough is. But the case that we'll focus on for today and tomorrow and going in the next later in the week is the situation where you actually do belong to the column space. If you do belong to the column space, then by belonging to it, there is some x that satisfies it, so there is at least one solution. And in that case, the system is referred to as consistent. And as we noted, it turns out that basically there's one of two possibilities. If you are in the column space, then either there are infinitely many possibilities, or there is exactly one, and it's split. It doesn't matter what you pick in the column space. Either everything in the column space will have a unique solution, or everything in the column space has infinitely many. So for home, if you're going to prove if there are two distinct solutions, then you can create infinitely many. And as we noted, the unique solution situation happens precisely when we have full rank. So when our matrix has exactly n linearly independent things in its column space. So when the rank is equal to n, which is also equivalent to the dimension of the null space equaling the trivial, the dimension of the null space being 0, so the null space being trivial. And then we worked out the details that we could basically focus on the null space case then, which is focusing on what's called the homogeneous system, where the right-hand side is the 0 vector. And then as we noted that anything that's a solution to the homogeneous is something that belongs to the null space. And the homogeneous system guarantees if we're going to have full rank and thus guarantee unique solutions. Quickly prove that, and basically a lot of this is just relying on the rank nullity theorem, which is nice. Good thing we proved it before we got here. That'd be terrible if a textbook would have done that. Oh man, I'm gonna bitch big time about the textbook. I absolutely hate the way they present this material in chapter 2. But anyway, all right. But then anyway, as we worked out the details last time, so the homogeneous system, the solutions that are non-zero are referred to the non-trivial solutions, and they only exist if you are rank deficient. So if your rank is not full, if you have rank less than n, then we can guarantee non-trivial solutions. All right, and we worked up the details there. Hey, the rank nullity theorem showed up. That's great. Okay. And we noted with that equipped, then in the situation where the columns outnumber the rows, then the homogeneous system will always have a non-trivial solution. So in that situation, you are rank deficient. Your rank cannot exceed m, and since that's strictly less than n, then you are rank deficient. So in fact, there are infinitely many solutions for anything you pick out of the column space, right? And it's quick proof. And now I noted that this proof, this is kind of one of the important proofs that you'll encounter in your life, because this is a rigorous, precise explanation for a mathematical feeling that you've always encountered. I have 3 unknowns and only 2 equations. As I just proven to you right here, there is no hope of solving this uniquely. So before you even work with this and create unique solutions, this tells you that, yep, your intuition was correct. Here's a solid proof. So one of the, right, if you were to, like I was talking about on Thursday, if you were to try to pick like the most important proof, I think this, it's not the most showy result. But in terms of justifying why we do proofs. I think this is a great one. Cool. All right, so we did that, and then we kept going. We noted that if you're rank deficient and you've got something in the column space, that are distinct solutions, and thus, in the rank deficient case, everything in the column space must have infinitely many solutions. Does not matter. And we know that there's an easy way to cheese it. You just, well, you're rank deficient, so there's a non-trivial solution. Take any solution to your column space and add the non-trivial homogeneous solution. That'll create a new solution, distinct from the first one we had. There we go. Yeah. So all of that together verifies that full rank happens precisely when the matrix equation can be solved uniquely for anything in the column space. This is the only time full rank happens. If there is something in the column space that has multiple solutions, your rank must be deficient, and vice versa. All right. And then we noted that there are some nice cases where we talk about the matrix equation always being able to be solved. If your rank is equal to your number of rows, then you can always be solved, and that's because rank equaling m happens precisely when the linear mapping induced by the matrix equation is on 2. And thus the matrix equation can always be solved. And then the follow-up to this was the real power here is that for square matrices, full rank is the bomb. Full rank means that we can always create unique solutions. And in fact, you can cheat with square matrices. If you can always solve the matrix equation, then it turns out that it must always be able to be done uniquely. So if you know that I can always solve, whether or not you know it's unique, it'll be forced to be unique in the square matrix situation. So that's an incredibly powerful tool that we're probably going to end up using. Probably when we talk about invertible matrix later this week. Right. So for square matrices, full rank is really, really what we want. So we will see that and talk about that, and it's going to be a good time. Right. So square matrices, love them. Right, full rank and having solutions ends up being a little bit more powerful. And this is another case, and we'll see it repeatedly, where the theory of square matrices is a lot nicer than the theory of rectangular ones. And in fact, the theory of square matrices opens up the door for what's called operator theory, as I've mentioned before, where somebody's like, I do operator algebras. What they really mean is, I look at square matrices, don't tell anybody. Yeah. I didn't realize that for the longest time. I was going to the conference and people just kept talking about like von Neumann operator algebras, and I was like, oh god, what is this nonsense they're speaking of? And then I was talking to my advisor, was like, what the hell are those? And he was like, they're just square matrices. I just want to sound like they're being impressive. Anyway, all right, so now we are up to speed. So here we go. Here is the big theorem. So if we have full rank, then if you want to solve ax equals b, well, there's exactly one x that's out there. And as we'll discuss, if you've got full rank, then what you're going to want to do is go after the inverse of the matrix, and we'll talk about that once we get the square later in this week. But for the rank deficient case, then it turns out that solutions, even though they are not necessarily uniquely solvable, they can be solved by first finding a basis for the null space and finding anything that solves the matrix equation. Then every solution is basically just a linear combination of things out of the null space plus some particular answer that you found. If you've taken differential equations, this hopefully looks incredibly familiar because that's exactly what you do in differential equations. Right. So in the full rank case, then there's a unique solution, and we'll talk about how to find that solution. We'll actually talk about that later in the section too, but the more cool way of doing it we'll do with invertible matrices. But in the rank deficient case, then it turns out that, well, even though you don't have unique solutions, we still have complete control over what solutions are going to look like. And this is pretty easy to do. So very surprisingly, maybe. So pick any solution to your matrix equation. Okay. Well, then you know AX is equal to B, and by hypothesis AP is also equal to B. Very well, we've seen this. Subtract this over. hey, x minus p, that must belong to the null space, so there is some scalars, multiples of the elements of the basis for the null space, so add the p over, and there you go. That's it. So, with this theorem in hand, we now have a blueprint to solve ax equals b for any possibility. So we've now proven what happens with float rank, and we have now proven what happens with rank deficient. All right, so we've got basically an algorithm now that we can follow. So what is it? So any consistent linear system can be solved. And it can be solved fully whether or not the rank is full or deficient, and here's how you do it. So you take your system and obviously rewrite it as ax equals b. Of course, one of the thing in the back of your head should be coming and being like, how would you even know if it was consistent to begin with without like just solving it? There's some tricks. We'll get to them. We will determine them. All right. But anyway. So the first thing you do is find a basis for the null space. So you look at the homogeneous equation and basically you try to solve it. And particularly you get a basis for it, and obviously we're going to want to know how to do that. We'll get to that. Then, after doing that, find anything that would solve the matrix equation. I don't care what it is, find something. Then two possibilities. If the null space is trivial, then congratulations, you're full rank, and your particular solution is the unique solution, and that's it. If you found a non-trivial basis for the null space, then you've got the general solution. Anything that solves ax equals b looks like this as per the previous proposition. All right, so that is it. That's the story for solving any consistent system of linear equations. Investigate the null space, find a particular solution. Two possibilities: trivial null space, you got your unique solution, so you're done. Null space is interesting. Well, oh well, you still have complete control over what all the answers look like. So, okay, but that of course leads us to the big question now of, all right, well, we did all the theoretical work. Now, how do you actually compute this crap? Okay. Well, it turns out that there's a nice systematic way of going about computing this crap, so let's talk about it. But first, we need a little extra piece of information. So step 0 to all of this. I realized I didn't prove this when we first brought up matrix multiplication, and that is proving that the identity matrix was chosen purposefully. So remember, the identity matrix is the matrix with 1 on the diagonal and 0 everywhere else. And the reason that's defined that way and called the identity matrix is because matrix multiplication and that particular matrix acts as an identity, specifically A times the identity matrix of appropriate sizes for our rectangular matrix here, A, will behave the way we want it to. Right. So we'll prove A, and it's pretty easy. So remember, the identity matrix has the property that its entries are 0 when the indices are different, and the entry is 1 when the indices are the same. So if you're to look at the matrix multiplication and look at the jkth entry, all right, well, you lock down your row, you lock down your column, then you run down. So in this case, it is m that we run to because I is m by m, so the inner dimensions are m. Right now in here, well, this zeroes out for any index that isn't j, so we pick up this, and as noted, ijj is 1, so we pick up the jkth entry of A. So there we go, multiplying by the identity matrix, it does not change the matrix, and now we see why we're calling it the identity matrix, because with respect to multiplication, it does not change the matrix, and that also reveals to us why our matrix has 1s on the diagonals and 0s everywhere else, rather than like a matrix just full of 1s, right? If this was full of 1s, it wouldn't eliminate, right? We have a summation. We need to eliminate all but one term. So there we go. Oh no, I dropped my mouse. All right. So turns out we're going to need this, so it's good to have this at our disposal. I was holding off on it. I know I didn't originally include it. I wanted to save it for talking about matrix inverses. But then when I was thinking about this material again and typing this up, I was like, great, I need the identity matrix. Should have proven that earlier. Oh well. But anyway, so there we go. Now, what are we going to use this with exactly? Well, it turns out that multiplying things by the identity matrix, as we see here, leaves the matrix unchanged. It turns out mildly modifying the identity matrix and then multiplying by it is a slick little thing. Now, before we get there, we need to introduce this idea of the row of a matrix. So we talked about the columns of a matrix. So given a matrix, you can create elements of Rm that consists of the row of the columns. We can do the same thing for the rows. Hopefully this isn't too surprising. This is showing up. Right, we had special notation for the columns. Obviously, we're going to have them for the rows at some point. Matrix is made up of rows and columns. And indeed, here we go. So the jth row then is the element of Rn. Remember, we lock down an M and run down, so there are N entries. And it's defined as you would expect. You lock down J, and then you let K run between 1 and N, and then you replace the asterisk with K. So the same notation I was using for the columns. Right, so for example, if I were to look at the matrix 1, 2, 3, 4, its second row is 3, 4. And now remember, elements of Rn, I will write vertically or horizontally, context dependent. We will take the stance that they are the same thing. You could also argue that Rn is isomorphic to the set of n by 1 and 1 by n matrices, but that gets real pedantic, so we won't deal with it that way. We'll just consider it as an element of Rn. All right. So we set up notation for the columns where we have the asterisk right here, and now we've got notation for the rows where we got the asterisk right there. All right, so now we'll combine the two things together, multiplying by the identity matrix and mildly modifying the identity matrix, because there are certain matrices that are very important that are built out of the identity matrix, and those are what are called the elementary matrices. So these are basically the building blocks of every matrix. And so we're going to define what they are, but the mentality you should have is that these are basically like the prime numbers for matrices. We're going to be able to use these to multiplicatively create any matrix we want. Well, any matrix, that's nice. So the three elementary matrices are as follows. Type 1 is swapping rows of the identity matrix. So here is formally how it's defined. You lock down two distinct rows, and the pth row of the elementary matrix is the qth row of the identity. The qth row of the elementary matrix is the pth row of the identity, and all other rows are left alone. So that is a type 1 elementary matrix. It is a modification of the identity matrix where two of the rows have been swapped. Type 2 is where one of the rows has been hit with a non-zero scalar. So some row has been replaced with alpha times the identity matrix, where alpha is a, and we need to stress here, non-zero entry. Multiplying a row by 0, and just that is going to be problematic, because again, we're going to use this to solve for the null space in particular solutions. And we're thinking about it in terms of systems. This is like, if this is non-zero, that means you're multiplying both sides of the equation by 0, which doesn't tell us anything interesting. It just get 0 equals 0. It's not interesting. Right, and then the final elementary matrix, the type 3, is the most involved one. You pick two rows, and you replace the qth row with itself plus a scalar multiple of the pth row, and all other rows are kept on 1. And now here we're allowed the scalar to equal 0 because we want the identity matrix to be an elementary matrix. specifically it's a type 3, you just pick any two rows, who cares, and then set alpha equals 0. That kills this, so hey, all the rows are just the identity. So here we do want to allow this to equal 0 to include the identity matrix as an elementary one. I've seen some textbooks make this non-zero, but then don't make the switching unique, distinct, where you can swap two rows and the rows can be the same technically. I think that's dumb, so I don't like doing that, but I have seen that where it's like, well, you make the identity a type 1, it's whatever. Right, it doesn't matter what you call type 1, type 2, or type 3. It's swapping rows, scaling a row, scaling and adding a row to another. You know, that is pretty consistent, though. If you look at like a lot of linear algebra textbooks, swapping is always type 1, scaling is always type 2, and scaling and adding a row is always type 3. So that's kind of interesting. That seems pretty consistent across the board. But the identity matrix as an elementary matrix, I've seen some people try to make it type 1 instead. I think that's dumb. Type 3 is fine. But anyway, well, now that I told you what they are, let's get some examples so we get like a good feel for what these things look like. All right, so hey, here's the type 1 elementary matrix. Note that I took the identity matrix, the 2 by 2 identity matrix, 1, 0, 0, 1, and I swapped row 1 and row 2. Here is a type 2 elementary matrix. I took the first row of the identity and multiplied by pi. There you go. Here is a type 3 elementary matrix. I scaled the first row by -2 and added it to the second. Now, note that this thing right here is not an elementary matrix. And how do you see that? Well, it looks like the identity matrix, but there is not just one row operation that, there's not, I used the wrong word. There is not one of the moves that gets you here. And by one, I mean explicitly one. Right? Because I could get here with two row swaps, right? I could swap row 1 with the bottom to get this one down there, and then swap the bottom with the middle to get here, right? But I needed to do 2. Okay. So elementary are the matrices that have one modification from the identity. This one has 2, right? It's got 2 row swaps that happen. It does not count as elementary. Right now, you let the word slip. The real power of the elementary matrices is multiplying a matrix by them, and that gives us what are called the row operations. So these are also called the elementary row operations. They're also broadly under the term of like the Gauss-Jordan algorithm or something like that. Basically, these are the elementary maneuvers that we can perform to a matrix that are nice. And basically, they are as follows. Given a matrix, I am able to multiply by a type 1 elementary matrix, which gives me the same matrix but with the rows swapped. If I multiply by a type 2, I get the same matrix but one of the rows has been scaled. And the type 3, I get the same matrix but one of the rows has been scaled and added to the other. So these are the elementary row operations. So there are 2 viewpoints to take with the row operations. There are the ones where you define them as functions on their own, that just like take a matrix and modify the rows, or you do it the way that I've done it, where you encode it as a matrix multiplication. That it is specifically multiplication by a specific matrix. I like this representation. Your book does not take this approach. One of the first blights against it, in my opinion. Treating the row operations as multiplication by an elementary matrix, I think, is the best way to go, because we have a lot of tools that we can use with matrix multiplication. So there's a lot of like theorems that we're able to kind of quickly explain by just going, hey, multiply by appropriate matrices, and you're done. If you have row operations as kind of their own separate entity, it gets a little dicey. Your book does do elementary matrices, though, as an appendix, so it is there. So check that out. But anyway, So multiplying by the appropriate elementary matrix gives me the row operation. So given a matrix, swapping its rows can be represented as a matrix multiplication. Scaling one of its rows is a matrix multiplication, and scaling and adding one of its rows is also in matrix multiplication. Okay, so rather than horribly bore you with all of the details of all three of these, let's just prove the one that's the most interesting, which is the type 3. And this is something that we're going to do repeatedly when we're doing elementary matrices, and basically just go, well, the type 3 is the most involved one, so let's actually prove that. All right. Okay. So how does this go? All right. Well, a type 3 elementary matrix, again, is one where one of the rows has been replaced by the original row plus a scalar multiple of another row. Okay. So that means if you're in any of the rows that are not equal to the index Q, well, then you just get the product of the identity matrix in A, which we have proven just gives you A. So there you go. So B, I don't know why there's parentheses around B. I felt like it, I guess. So for any of the rows that are not equal to Q, then multiplying by the elementary matrix does not change the matrix at all, which is what we expect. We only expect that the Qth row is the one that has been changed. Okay, so now if we look at the Qth row, well, the Qth row is, for our elementary matrix, is the Qth row of the identity plus alpha times the Pth row. All right, well, these are equal to 0 whenever your index is not in there, right? Because if it's not P and it's not Q, well, it's not Q, so this is 0. It's not P, so this is 0. So that means the elementary matrix is always equal to 0 for any index H that's not in P and Q. So that means if we look at the kth entry now in the Qth row, all right, well, that's B is equal to E times A, and we're looking at the Q for kth entry. That gives me, well, all of the non-P and Q entries zero out and go away. And then now here, all right, differing indices, so that will be a 0 and that will be a 1. So I'll pick up an AQK. This here will be a 1 and that will be a 0, so I'll pick up alpha A PQ. So in other words, the Qth row of this matrix B, which is the elementary matrix times A, is the Qth row of A plus alpha times the Pth row of A. So exactly as claimed. So multiplying matrices by specific elementary matrices give us these row operations. So given a matrix, if you want to swap two rows, well, multiply by the appropriate elementary matrix. Given a matrix and you want to scale a row by a non-zero scalar, well, multiply by an appropriate matrix. And likewise, if you want to scale a row and add it to another, there is an appropriate matrix you can multiply it by. All right, well, talk is cheap, so let's see some examples so we get a feel for it. All right, so, all right, hey, here's a nice matrix, 1, -2, -3, 4. Let's perform some row operations to it. Okay, so a type 1 would be swap the rows. There we go. Now, I know that this was actually multiplying this matrix by the appropriately modified identity matrix. So multiply it by the elementary matrix 0, 1, 1, 0. That will give you this. We just proved that that has to be the case. We didn't prove that. Okay, a type 2 row operation. So one of the rows has been scaled by a non-zero scalar. So here we scaled the top row by -pi. And the same effect can be accomplished by multiplying this by the matrix whose top row is -pi, the same operation. And this right here is a type 3 row operation where I multiplied the top row by 3 and added it to the bottom row. So the same effect can be accomplished by taking the identity matrix, doing the same thing, and multiplying it to the matrix. So here are the 3 row operations, the 3 elementary row operations. It's all a good time and all good fun stuff. All right, so we've now got the row operations at our disposal, which are just multiplications on the left by a very specifically chosen matrix. So this naturally leads to, all right, well, how does this all tie in to actually solving for the null space and solving for particular solutions? All right. Well, let's answer the first one. How can we use this to help us figure out what's going on with the null space? All right, well, turns out that the secret ingredient to that is that elementary matrices can be undone. So those operations we just discussed, swapping two rows, scaling a row by a non-zero scalar, now you're seeing the non-zero part being important, and scaling a row and adding it to another, all of those can be undone to get you back where you started, and that is equivalent to saying that given an elementary matrix, there is another one so that the product of those two gives me the identity. And again, we'll prove it for type 3 and note that you can do the same thing for type 1 and type 2. The details here are kind of excruciating, but they're not the worst. All right. So let's say E is a type 3, so it's got distinct rows and a scalar. Well, then a type 3 that looks almost exactly the same, only now the scalar is negative alpha, will undo it. Indeed. If you look at the Q row, all right, well, the Q row of L times E, as we proved, multiplying by an elementary matrix gives you precisely this. All right, and well, what do we know about E? Well, E has been rigged to look like that. And oh, hey, we get the Q row of the identity matrix. Alpha, negative alpha, they delete each other. There we go. And the H row of L times E gives me the H row of E, which is the H row of the identity matrix. So there you go. L times E is indeed the identity matrix. So in fact, you can actually state something a little bit more. The elementary matrix that undoes your elementary matrix and gets you back to the identity is always of the same type. Right, so given a type 1, you can undo it with another type 1. Given a type 2, you can undo it with another type 2. And it's worth stressing there that that's why you need the non-zero. If it is 0, then you can't undo it. If you scale by 0, you kill a whole row. You can't bring it back to its original form. Because you would just be multiplying zeros. There's no hope of creating it. Nice. So this is just saying that row operations can be undone. So if you swap rows, you can just reverse the swap. If you scale by a non-zero, well, then you can just scale by 1 over it. And if you scale and add a row, as you can see here, well, then just scale and add the negative of the row. It'll get back to normal. Beautiful. So this is the real power for elementary matrices. The fact that we can undo them. Right. So the fact that row operations can be done and undone is the real secret to why the sense of being the right sort of tools to find a basis for the null space, and solve for particular equations. Okay, so to formalize that and get there, we have to introduce this idea of row equivalence. So two matrices are said to be row equivalent if I can find elementary matrices, P of them, so that the product of those elementary matrices times A gives me the matrix B. And the appropriate way of thinking about this is that I can turn A into B using a finite number of row operations. Right, so in your homework, one of the problems is I'm going to give you two matrices, and then I'm going to ask you verify that these are row equivalent. So in other words, show me what are the elementary matrices that get you there. So what are the row operations you need to perform to turn A into B? There's a trick with that one, but you can brute force it. It's not too hard. Simultaneously do it. Take A and B in the start, just converging to a singular one. And by the following, you can get the row equivalence pretty easily. So anytime you see the word equivalent in mathematics, that means that probably an equivalence relation is afoot. And remember, an equivalence relation is a relation so that everything is related to itself. If something is related to something else, then you can reverse the order. So I can say A and B are row equivalent, and that means something, because it doesn't matter which direction the equivalence goes in. And finally, if A is equivalent to B and B is equivalent to C, and then we've got transitivity, A is equivalent to C. So what the trick for the homework is, rather than trying to directly show A can be turned into B, turn A into a matrix and then turn B into the same matrix. Then, right, you've got your waypoint to get them equivalent. That's the quick way of doing it. If you want to directly turn A into B, you can, but it's more steps. There's a cheat. Talk a little more about that. But anyway, okay. And again, as noted, Part B lets us say A and B are row equivalent, and that is meaningful. Right. Note the way the definition is set up is that A times stuff equals B, so that has an ordering to it. But as we will prove, it actually doesn't matter. All right, so now here we go. As we've noted, the identity matrix is a type 3 elementary matrix, so there we go. And now here's why you need the identity matrix to be an elementary matrix. Otherwise, this part of the proof, you can still do it if you don't include the identity matrix as a elementary one, but it's like stupid. It's like pick any elementary matrix and then multiply by the elementary matrix that undoes it, then you get the identity matrix. So you might as well just set it up so the identity matrix is a row operation. My opinion on it, of course. All right, so the identity matrix is an elementary matrix, so A is equivalent to itself, right? Perform no row operations. There you go. So if A is equivalent to B, then there are a finite number of row operations that turn A into B. Okay, well, we can always undo the row operations. So then apply them to B, you'll get back to A. Ta-da. Right, and so note, you got to do them in reverse order, right? So you take A, row operation 1, row operation 2, all the way up to the Pth one. Then if you want to go backwards, back to B, well, then you need to do the inverse row operation of P, then the inverse operation of P minus 1, all the way down to the inverse operation of 1. So if A gets mutated into B, then you could just do the row operations backwards, and you'll get it. And pretty easily, if A is equivalent to B and B is equivalent to C, then I've got row operations that make A into B, row operations that make B into A. So just hit A with all of them, and you'll get the C. And that's it. So row equivalence. There you go. Two matrices are row equivalent if row operations turn them into each other. And now that we've got this and we're equipped with this, we can now actually start proving things that are going to reveal that row equivalence is the bomb, and it's the coolest thing ever, because row equivalence does not screw up the important stuff about a matrix. That's why it exists. All right, so let's start working on that. So specifically, the first thing we'll prove, well, of course, as we've discussed, when it comes to solving for the null space of a matrix, finding a basis for it, we want to do that to solve any matrix equation. And now, as we'll prove, every elementary matrix does not mess up your null space. If you have a matrix and then you perform a row operation to it, you multiply it by an elementary matrix, you did not change the null space. So equivalent matrices have the same null space. That's right. All right, so let's prove this. And I'm going to note here that because I'm viewing row operations as matrix multiplication, this proof is super easy. If you viewed row operations as just that, like an operation, a function on the set of matrices, this proof is way more of a pain in the ass. But treating it as matrix multiplication, the correct way of doing this, this is for free. Right? Pick anything in the null space, that means A times X is equal to 0. Well, multiply it by E. There you go. Matrix multiplication is associative, and multiplying by 0 just gives you 0. So, hey, you're in the null space of E times A. All right. So if you were in the null space, then any modification that you performed to A keeps you in the null space. And vice versa. Let's say you are in the null space of a matrix that's been hit with a row operation. Okay, well, that means EA times X is equal to 0, but as we noted, every row operation can be undone. So now multiply by the reverse row operation, multiplied by the reverse elementary matrix. All right, well, AX then, which is equal to I times AX. I is equal to L times Z. The associativity allows me to move around the parentheses. We have this equals 0. Hey, L times 0 is indeed 0. Plus you're in the null space. Boom. So, row operations do not change my null space. That is very good news. Why is that very good news? Because that now means, as I noted, any two row equivalent matrices are going to have the same null space. And with that, we then end up getting that if you've got two row equivalent matrices, their rank must be equal. So rank is unaffected by row operations as well. Oh, that's really powerful, isn't it? Especially if, I don't know, I were able to convert my matrix into a really nice matrix where it's super easy to detect the rank, like counting the number of non-zero rows or something. Oh, yeah, oh, whatever. Anyway, so let's prove this. All right, so A is equivalent to B, so there's some row operations that turn A into B, right? And as we just proved, the null space of a matrix multiplied by an elementary one does not change. So B is equal to A times a bunch of elementary matrices. Well, as we just proved, you can peel one of them off. And there's finitely many, so keep peeling them off until you get down to the null space of A, and hurrah! Two row equivalent matrices must have the same null space. So if I have a matrix and I want to figure out a basis for the null space, probably want to hit it with a bunch of row operations until it becomes a matrix that is super easy to find a null space of, right? Rather than trying to find the null space of the original, more complicated matrix, just smash it with a bunch of row operations until it behaves. Sounds like a good idea. All right, and now equipped with this, the rank nullity theorem now tells us the following. Given any two row equivalent matrices, they have to have the same rank. Right? We now have proven that their null spaces are the same. So by rank nullity, these are the same and they cancel out, and thus we get rank A is equal to rank B. That's nice. So it is worth noting that rank does not get changed by any row operations. However, the column space does get screwed up. All this says is that the dimension of the column space doesn't change. So unfortunately, you can't use row operations to figure out a basis for the column space, because row operations will scramble them. There's a trick that you can pull off with the transpose. I'll talk maybe a little bit about it. I was going to originally include that as something for us to prove, but it really has no bearing on anything else in this course. There's some other things too that I'm not going to touch it, and I'll talk about it. But anyway, so equipped with this, we now have a way forward for actually computing a basis for your null space. You actually now have a way of doing it. Specifically, all right, take your matrix, hit it with row operations until we get a matrix where the null space is easily detected. Right, so a situation where computing the null space is just, well, multiply it by x and set it equal to 0, and basically you can just read off what the answer is. So specifically, the form that we're going to want to get that matrix in is a form that you may have encountered before and may have heard of, and that's Echelon Form. Okay, so Echelon Form is easy to describe to somebody. It's terrible to define. So here is the formal definition for Echelon Form, and then I'll tell you what it intuitively means. So formally, you're an echelon form if the following happens. Given two rows, so that one row is non-zero and one row is 0, then the non-zero row comes first. Okay. So another way of thinking of this is that all of the 0 rows are at the bottom of the matrix. And then the next one, given non-zero rows, so that one row is above the other, then the smallest entry where you have a non-zero is to the left of the smallest non-zero entry in the row below it. So exactly what I said. So all of the 0 rows are at the bottom of the matrix, and the first non-zero element in a row is always strictly to the left of any non-zero entry below it. So basically, all your zeros are at the bottom, and there's a descending sort of staircase pattern going on. And so we'll get an example of this in a moment here, but the big thing is that every matrix can be turned into a matrix in echelon form. Here's my proof. Do row operations. I want to stress here, I have never seen a proof of this that I felt was like even reasonable. I sat down and tried to prove this, and as far as I can tell, it's basically just like inductions inside of inductions. So what you would do is basically go, well, step one, okay, if there are any zero rows that aren't on the bottom, then perform type 1 row operations until they're all on the bottom. And then you would then need to, with the non-zero rows, sort of arrange them so that there's a staircase pattern, and if there isn't, then you need to perform type 3 row operations to delete stuff below it. It's, oh my god, I've never seen a proof of this. That isn't basically just, well, you do row operations until you get it. And let's finish up today with some examples. So here is something in echelon form, all the zeros at the bottom, and like I discussed, there's this staircase pattern going. Same thing here. There are no zero rows, so we're happy, but note that there is the staircase pattern. Now here, it occurs 2 steps over rather than just go down, 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 but that's fine because the only requirement is that the leading non-zero entries are descending and moving to the right. Right, so we don't have a 3 down here. If I did have a 3 here, then you perform a row operation to delete it. Okay, and these ones are not in echelon form. This row is all zeros, that needs to be at the bottom. And this one violates our descending staircase rule. Right, we have 1, then we go to 3, but then we jump to the left. We can only move to the right. That's our goal with the echelon form. So it's worth noting that I don't consider the leading coefficient having to be 1 as part of the definition. Some people take that as part of it where they want the leading entries all equal 1. You can get that from a type 2 operation, just scale them out. But I don't, I'm not too sweaty about that. If you don't want to do that, that's fine. I don't. If you want to include it, go ahead, but otherwise, fine. All right, so there we go. We have now discussed performing row operations and row equivalence. All right, and we've now got echelon form down, and we've proven that every matrix can be turned into an echelon one. And now what we're going to verify is that we want to be in echelon form, because if we are, then the null space is super easy to construct. And once you get your null space, then you can pick up a bunch of other things for free, and that's what we'll talk about next time. All right, so that is it for today. Stop recording.